Now coming to Van model equations. Here we have to consider the RT x1 x2 by G is equals to A dash plus B dash into x1 minus x2. Previously we know that G by RT x1 x2 is equals to A plus B into x1 minus x2. Just reverse that equation in Van model. RT x1 x2 by G is equals to A dash plus B dash into x1 plus A dash minus B dash into x2. Multiply A dash B dash with x1 minus x2. Therefore, RT x1 x2 by G is equals to x1 by A21 dash plus x2 by A12 dash. Here, assume A21 dash is equals to 1 by A dash plus B dash. Similarly, A12 dash is equals to 1 by A dash minus B dash. Here in this model, RT x1 x2 by G is equals to A dash plus B dash into x1 minus x2. Just multiply A dash plus B dash into x1 x2. Therefore, A dash plus B dash into x1 plus A dash minus B dash into x2 here. Let A21 dash is equals to 1 by A dash plus B dash. A12 dash is equals to 1 by A dash minus B dash. Now taking LCM here. RT x1 x2 by G is equals to A12 dash x1 plus A21 dash x2 divided by A12 dash A21 dash. Then reverse this equation. Therefore, 1 by f this expression G by RT is into x1 x2 is equals to A12 dash A21 dash divided by A12 dash x1 plus A21 dash x2. Therefore, taking right hand side of x1 x2 to left hand side, therefore G by RT is equals to A12 dash A21 dash x1 x2 divided by A12 dash x1 plus A21 dash x2. We know that mole fraction x1 is equals to n1 by n. Similarly, mole fraction of species 2 is equals to n2 by n. Number of moles of second species divided by total number of moles. Therefore, G by RT is equals to A12 dash A21 dash into N1 N2 by N square divided by A12 dash into N1 by N plus A21 dash N2 by N. Therefore, G by RT is equals to A12 dash A21 dash N1 N2 by N into A12 dash N1 plus A21 dash N2. Taking this n term to right hand side of this equation. Therefore, Ng by RT is equals to A12 dash A21 dash N1 N2 by A12 dash N1 plus A21 dash N2. Now differentiate Ng by RT with respect to L. That is equals to ln gamma 1. It is in the form of U by V formula. U by V differentiation is V U dash minus U V dash divided by V square. That is A12 dash A21 N2 is constant. N1 differentiation is 1 multiplied with V. That is A12 dash N1 plus A21 dash N2 minus U into V dash. Here U is the A12 dash A21 dash N1 N2 multiplied with V dash. That is A12 dash N1. Differentiation of A12 dash N1 is A12 dash. that is minus A12 dash A21 dash N2 N1 A12 dash. This is the differentiation with respect to N1. After that, eliminate the term A12 dash A21 dash N2 into A12 dash N1 plus A21 dash N2 minus N1 A12 dash by A12 dash N1 plus A21 dash N2 whole square. Here A12 dash N2 is the remaining term. A12 dash N1 minus A12 dash N1 gets cancelled. Therefore, A12 dash A21 dash into A21 dash. Therefore, A12 dash A21 dash whole square N2 whole square the remaining term. Then divide with A21 dash whole square. After dividing with A21 dash whole square, this is the resulting equation. That is equals to A12 dash N2 square divided by A12 dash N1 by A21 dash plus N2 whole square. Then divide with N2 square. I am taking the term N2 square to denominator, that is A12 dash divided by A12 dash N1 by A21 dash N2 plus N2 by N2 whole square. Therefore, ln gamma 1 is equals to A12 dash into A12 dash N1 by A21 dash N2 plus 1 power minus 2. Taking the denominator term into numerator, that is equals to minus 2. Similarly, differentiating with respect to N2, ln gamma 2 is equals to A21 multiplied with A21 dash N2 divided by A12 dash N1 plus 1 whole power minus 2. These two are called as Van equations. Now coming to property changes of mixing. Property changes of mixing is defined as delta M is equals to M minus sigma xi mi. Delta M is equals to M minus sigma xi mi. Here M is the molar solution property, Mi is the molar pure species property. Delta M is the property changes of mixing. Equation A is called as property changes of mixing. Here excess Gibbs energy is represented by Ge is equals to G minus sigma Xi Gi minus RT sigma Xi ln Xi. Then G is equals to delta G minus RT sigma Xi into ln Xi. Delta G is equals to M minus sigma Xi Ga. That is coming from property changes of mixing. Here delta G is the Gibbs energy changes of mixing. Similarly, we have to write for entropy. Therefore, excess entropy is equals to S minus sigma Xi Si plus R into sigma Xi ln Xi. Excess entropy is equals to delta S plus R sigma Xi ln Xi. Here delta S is coming from property changes of mixing. That is delta S is equals to S minus sigma Xi Si. Delta S is the entropy changes of mixing. For excess volume, which is represented by VE is equals to V minus sigma Xi Vi. Therefore, V is equals to delta V. Delta V is equals to V minus sigma Xi Vi, which is coming from property changes of mixing. Here delta V is the volume changes of mixing. For excess enthalpy, He is equals to H minus sigma Xi Hi. Therefore, He is equals to delta H. H means excess enthalpy. Delta H is coming from property changes of mixing, which is equals to H minus sigma Xi Hn. Here delta H is the enthalpy changes of mixing. Here consider ideal solution. For an ideal solution, excess property is 0. Therefore, in G is equals to delta G minus sigma Xi ln Xi equation, G term gets cancelled. Therefore, delta G is equals to RT sigma Xi ln Xi, which is written for ideal solution means delta G ID is equals to RT sigma Xi ln Xi. Similarly, for entropy and enthalpy and volume, all SE, HE, VE terms gets cancelled because excess property is 0. Therefore, delta SID is equals to minus R sigma Xi ln Xi. Similarly, delta HID is equals to 0. Delta VID is equals to 0. Property changes of mixing can be written for an ideal solution is delta MID is equals to MID minus sigma Xi Mi, which is indicated with equation B. Property changes of mixing definition can be written for ideal solution, that is equals to delta MID is equals to MID minus sigma Xi Mi. Subtract equation B from equation A. That is property changes of mixing for an ideal solution subtracted from property changes of mixing equation. Therefore, delta MID minus MID plus sigma Xi Mi is equals to delta M minus M plus sigma Xi Mi. Therefore, sigma Xi Mi gets cancelled on both sides of the equation. Therefore, delta MID minus MID is equals to delta M minus M. Delta M minus delta MID is equals to M minus MID. Therefore, from the definition of excess property, M minus MID is equals to ME. Therefore, ME is equals to delta M minus delta MID. Before going to the experimental mixing process for binary system, we are discussing about some background of the topic. That is, we know the equations G is equals to delta G minus RT sigma Xi ln Xi. Similarly, SE is equals to delta S plus R sigma Xi ln Xi. V is equals to delta V. HE is equals to delta H. These equations show that excess properties and property changes of mixing are readily calculated one from each other. If excess property knows, automatically calculate the property changes of mixing. Although historically property changes of mixing were introduced first because of their direct relation to the experiment data. Excess properties fit more readily into the theoretical framework of solution thermodynamics. Because of their direct measurability, delta V and delta H are the property changes of mixing of major interest. Why? Because P is equals to delta V, directly related excess property, and delta V. Similarly, delta H is equals to HE. There is no complexity and there is no other properties involved in this VE and HE. Because of their direct measurability, delta V and delta H are the property changes of mixing of major interest. Moreover, they are identical with the corresponding excess properties. They are identical with the corresponding excess properties. Now we are discussing about experimental mixing process for a binary system. Here consider two pure species. Both are separated by some partition. Pure species are N1 and N2. Both the species are at uniform temperature and pressure. Here P is the pressure applied on the species, that is piston arrangement. Then remove the partition. After removing partition, the species N1 and N2 are mixing together. Therefore, the second diagram shows the mixing of species 1 and 2. After mixing, either expansion or contraction occurs, which is shown in figure 2, which shows expansion. That means the partition moves to some position. The difference between before mixing and after mixing is D. Here pressure is constant, so which allows either contraction or expansion. So the movement of piston carries the expansion or contraction of the system. Here temperature is constant. Therefore, to maintain the constant temperature, heat is added or extracted from the system. When mixing complete, the total volume change of the system is represented by total volume change, that is delta Vt is equals to N1 plus N2 into V minus N1 V1 minus N2 V2. Therefore, divide the total volume with N1 plus N2, that is equals to delta V total divided by N1 plus N2 is equals to V minus N1 by N1 plus N2 into V1 minus N2 by N1 plus N2 into V2. Therefore, delta V, that is equals to total volume by total number of moles is equals to delta V, that is specific volume is equals to total volume by number of moles, that is equals to V minus x1 into V1 minus x2 into V2. Here x1 is N1 by N, that is mole fraction of species 1. N2 by N is mole fraction of species 2, that is equals to x2. Therefore, delta V is equals to V minus x1 V1 minus x2 V2. Therefore, V is equals to delta V plus x1 V1 plus x2 V2. Now, we have to calculate total heat transfer is equals to delta H total is equals to N1 plus N2 into H minus N1 H1 minus N2 H2. For constant pressure process, Q is equals to change in enthalpy. That's why Q is equals to delta H total is equals to N1 plus N2 H minus N1 H1 minus N2 H2. Therefore, divide the equation with N1 plus N2 on both sides. Therefore, delta H total divided by N1 plus N2 is equals to H minus N1 by N1 plus N2 into H1 minus N2 by N1 plus N2 into H2. Therefore, total enthalpy divided by total number of moles is equals to specific enthalpy, that is equals to delta H is equals to H minus x1 H1 minus x2 H2. Here x1 is the mole fraction of species 1, x2 is the mole fraction of species 2, that is equals to N1 by N and N2 by N. Therefore, H is equals to delta H plus X1 H1 plus X2 H2. The property changes of mixing and enthalpy changes of mixing are found from measured quantities, total volume change and total enthalpy change. That means delta H and delta V are calculated from total enthalpy change and total volume change. Because of its association with Q and delta H is called the heat of mixing. Now coming to heat effects of mixing process. We know that property changes of mixing delta M is equals to M minus sigma Xi Mi. The heat of mixing delta H is equals to H minus sigma Xi Hi. It gives the enthalpy change when pure species are mixed at constant temperature and pressure to form 1 mole of solution. For a binary system, delta H is equals to H minus sigma Xi Hi. Therefore, for a binary mixer, H is equals to delta H plus X1 H1 plus X2 H2. These formulas are helpful for solving the problems on this chapter. This equation is used for calculation of enthalpies of binary mixers from enthalpy data for pure species 1 and 2 and from heat of mixing. So heats of mixing are similar to heats of solution. Now coming to heats of solution. When solids or gases are dissolved in liquids, when solids and gases are dissolved in liquids, the heat effect is called heats of solution. And it is based on the dissolution of 1 mole of solute. Heats of solution is based on the dissolution of 1 mole of solute. If species 1 is the solute, then X1 is the moles of solute per mole of solution. Here X1 is the moles of solute per mole of solution. Delta H is the heat effect per mole of solution. Therefore, delta H by X1 is the heat effect per mole of solute. Therefore, heats of solution delta H is equals to delta H by X1. Here, delta H bar is the heat of solution on the basis of the solute. Thus, delta H bar is equals to delta H by X1. Here, delta H bar is the heats of solution on the basis of molar solute. Now coming to local composition models. Theoretical development in the molecular thermodynamics of liquid solution behavior are often based on the concept of local composition. Molecular thermodynamics of liquid solution behavior, which is represented on the basis of local composition. Within a liquid solution, local composition different from the overall mixer composition are presumed to account for short range order and non-random molecular orientations, which results from differences in molecular size and intermolecular forces. The concept was introduced by G.M. Wilson. Alternate equations in correlation of VLE data, that means vapor liquid equilibrium data, are NRTL, which is non-random to liquids, and uniquark, that means universal gaseous chemical equations. alternate equations incorrelate the real data, that means XY data, are NRTL and univac equations. Here, univac equation is developed based on univac equation. It is used to calculate activity coefficient from contributions of the various groups making up the molecules of the solution. Now coming to Wilson equation for binary solution. Binary solution containing two parameters. Therefore, GE by RT x1 x2 is equals to minus x1 ln x1 plus x2 into delta 1 2 minus x2 into ln x2 plus x1 delta 2 1. Therefore, ln gamma 1 is equals to minus ln x1 plus x2 delta 1 plus x2 into delta 1 2 divided by x1 plus x2 delta 1 2 minus delta 2 1 divided by x1 delta 2 1 x1 delta 2 1 plus x2. For finite dilutions, the equation becomes ln gamma 1 infinity is equals to minus ln delta 1 2 plus 1 minus delta 2 1. Similarly, for infinite dilutions, ln gamma 2 infinity is equals to minus ln delta 2 1 plus 1 minus delta 1 2. Here, delta 1 2 and delta 2 1 are positive equations. Now coming to NRTL equations. Here consider G by RT x1 x2 is equals to G21 tau 21 divided by x1 plus x2 G21 plus G12 tau 12 divided by x1 G12 plus x2. Therefore, ln gamma 1 is equals to x2 square into tau 21 G21 by x1 plus x2 G21 plus tau 12 G12 by x2 plus x1 G12 whole square. Similarly, for ln gamma 2 is equals to x2 square tau 12 G12 divided by x2 plus x1 G12 whole square plus tau 21 into G21 by x1 plus x2 G21 whole square. For infinite dilutions, ln gamma 1 infinity is equals to tau 21 plus tau 12 exponential of minus infinity tau 12. Similarly, ln gamma 2 infinity is equals to tau 12 plus tau 21 exponential minus alpha tau 21. Here, the local composition models have limited flexibility in the fitting of the data, but they are adequate for most engineering purposes. That means they are not used in most of the engineering applications.